All right, so let's do a little bit of talking about the least squares solutions that you should have watched a little bit about the video. Anyway, so we're talking about least squares. We're talking about trying to find a solution to a system of equations. However, that system, the original system, probably not consistent. So the whole idea behind this is to try to find as good as possible of a solution to the system, as opposed to finding the exact solution to the system. So, when we for a linear system that we have for ax equals b, whenever we find that vector for substituted for x, the thing that actually minimizes that particular magnitude is what we refer to as a least squares solution to the original system. That's what we mean by a least squares solution. So anyway, the idea behind this, of course, is that if we think about this ax, if we think about it from a graphical perspective, this is basically linear combinations of the columns of A. So if I think about, I like to draw my subspaces as planes because that was interesting. It actually just changed it to a space or a shape. It changed it to a rhombus. Apparently it did an automatic substitution there. That was weird. Anyway, it's doing all sorts of things. It actually made that a circle. Okay, sorry, just got distracted there. All right, so let's say that this is the column space of A. So this is our W. This is what this is representing. Ideally, our B would be down here in the space, right? This would be kind of the ideal. However, probably it's sticking out this way and not on. This is really bizarre. And not in the subspace itself. It's probably above the subspace. I have no idea. Oh, it's doing ink to shape. Let's turn that off. That's annoying. So it's sticking up off of the subspace, most likely. So we're trying to find the solution that's the best solution to this system. So it's probably not in the subspace. It's probably sticking off this direction. So to find the best solution, we're going to drop down, like we've talked before, and look at that projection onto the subspace. So that's the idea that we're looking for. So to find this vector, we create what we refer to as the normal system, the normal system associated with this. And how did we, went through that in the video, but how did we come up with that? So let's talk about how we come up with that. We're trying to solve the AX is equal to the projection now of B onto W, because we know the projection actually is in the column space. We'll subtract B from both sides, or subtract both sides from B, I should say, the other way around. And then the reason we do this is because this vector on the right-hand side is the one that's sticking up. This is the one going this direction. Okay, so this is perpendicular to everything in A. So if we multiply, if we know that it's perpendicular in everything in A, and we know that if it's it's perpendicular to everything in the column space of A, we know that the column space of A is the same thing as the row space of A transpose, which is the orthogonal complement to the null space of A transpose. That means that if I take anything that's in the column space, it's orthogonal to anything that's in the null space of A transpose. So since this is orthogonal to the column space of A, it's the one that's pointing straight up, it has to be in the null space of A transpose. So if we multiply both sides by A transpose, this vector on the right-hand side has to be equal to 0. And again, that's because the B minus the projection we know is orthogonal to the subspace. Any vector that's orthogonal to the column space of A is in the null space of A transpose because that's its orthogonal complement. Now we can rearrange this equation to get A transpose AX equals A transpose B. So this is your normal system. Okay. All right, we know that this system is always consistent because we can always project this vector down into the column space. So we can always solve this without any question because we know, in particular, we know that the projection is in the column space. It's the whole idea of doing the projection, right? So we know that the projection's in the column space so that I know that it's always consistent and it's going to have a unique solution when what happens? Well, if I want to get x by itself, I need to be able to take the inverse of that matrix. So this will be have a unique solution when A transpose A is invertible. And it turns out that this is equivalent to A having n linearly independent columns. And I can't remember at this present time if I included the proof of that in the last video or not. They give you a proof of the fact that if it has linearly independent columns, then the matrix is invertible. That proof, this direction proof, whoa, that's not even a good looking direction. This direction, my goodness gracious, I can't write. This direction is on page 334. All right. So of course then, if I want to try to find the solution, then I just need to multiply by the inverse. So the solution to this system is A transpose A inverse times A transpose times B. So this is the least squares solution in this case. If we want the orthogonal projection onto the column space of A, then we just need to multiply both sides by A. So this will just be AX, because that was equal to the projection of B onto W. So then we would have A times A transpose A inverse times A transpose times B. So these are the two big things to remember as far as the formulas go for being able to solve these problems. All right, so let's find answer the first question here. It says find the orthogonal projection of U onto that subspace that's spanned by V. All right, so I make a matrix A. I want to project this onto the column space of A. So if I want to make a column space of A, I'm going to put those vectors as columns in A. So I put the 1, 1, 0 down the first column, the 1, 2, 1 down the second column. Okay. This means that I've created a matrix where we're going to do the column space. So if I use that previous formula we just came up with, I know the projection of U onto the column space of A. So W here I'm going to use to denote the column space of A. This is going to be our A matrix times the A transpose A inverse times A transpose times B, where our B here, this is going to be our vector 2, 1, 3. Looks like a lot of calculations to do, so this looks like a great job for the calculator. So let's go flip over here. So I'm going to go to matrix A. I'm going to edit matrix A. Maybe I'm going to edit it. Matrix A was 2 columns and 3. Oops, sorry. No, it wasn't. It was 2 columns. It's just that's not the column number. It was 3 rows and 2 columns. The first row had a 1 and a 1. The second row had a 1 and a 2. And the third row had a 0 and a 1. And then it's go back in and put in a B. Actually, I'll make it H because I don't want to mess up what I'm doing with other things that I want to show you later. Matrix, edit, H. That's a 3 by 1. And the vector was 2, 1, 3. So the formula is we do A times A transpose times A. Oops. And then do the inverse. And then multiply by A transpose. A lot of typing in the calculator here. And then times B, which was actually an H. And why is it telling me invalid? Don't know why it's telling me invalid. Let's see here. Matrix. Let's just see if I can do A transpose. Okay, so I did A transpose. Why is it telling me it was invalid? Let's see here. Let's try this again. A transpose. Sorry about the delay here. I don't know why it's not doing what it's supposed to be doing. Okay. So, all right. So, and then if I do A times that, I don't know why it's not, why I didn't do it before. A. Oops. I need to do the inverse of that. So let's do the answer inverse, which is no problem doing. Now let's do the matrix A times that answer. And then I have no idea why it didn't do it the first time when I typed it all in. A transpose. And then times B. Okay. Apparently it didn't let me typing it all at once. I have no idea why not. All right, anyway, there's your solution. And again, if you really like to see this as fractions, you can. So we get 2/3, 7/3, 5/3. So this will be 2/3, 7/3, 5/3. That's the orthogonal projection. All right. So let's see what we have in the pictures, if you will. So our vector, the plane down here, the W, that's representing the plane that was generated by the two vectors V1 and V2, the 1, 0, 0 and the 1, 2, 1. And then my vector U is the one sticking up off of there. So this projection of U onto W is that one there. That was what we just found. And it was 2/3, 5/3, 2/3, 7/3, 5/3. So it comes out a little bit, 2/3. So this is actually off the plane this way, and then over 5/3 and or up over 7/3 and up 5/3. Maybe up 5/3 is a little bit easier to see here because 5/3 would be a little bit short of 2, right? So you can kind of see the 5/3 there. If I go straight down here, you can see the 7/3 this way, and then the 2/3 out this way, if you will. So you can kind of see it off the whole idea was there. I wanted to show you that it was it's in the plane. It's just kind of where the coordinates were. All right, anyway, I just thought the picture might help with what we were actually finding. The W is representing the subspace that we have, and then this is your vector U. This is your vector W, or your vector of the projection. This is the difference of those two. That would be orthogonal projection. You can actually see the orthogonal piece there. That was why I put that in there. All right, let's do another one. let's say we want to find the cubic polynomial that best fits these points. All right, so the first thing we need to remember is that a cubic polynomial has the following form. It's ax cubed plus bx squared plus cx plus d. All right, so this is linear in its coefficients, so that's important to be able to use least squares method if we're trying to solve a linear system. What we need to solve for are the constants a, b, c, d. So it needs to be linear in those constants. That's important. It's not, we're going to plug in things for the x. So the fact that that's not linear is perfectly fine. It's the a, b, c, d that we need to be linear because we want to come up with a set of linear equations. All right, so the idea here is when we plug in -1, we're supposed to get out 7. When we plug in 0, we're supposed to get out 2, and so on down the line. So the system we get would look like what? -a plus b minus c plus d equals 7. That's what we would have if we plug in -1 for x. You would also get d equals 2 and d equals 1. That's when we plug in 0 for x, we get both of those outputs. When we put in 1, we would have a plus b plus c plus d equals -2. When we put in 2, we would have 8a plus 4b plus 2c plus d equals -1. Again, when we plug in 2, I get the same left-hand side. But we get -2 on the right-hand side. And then finally, the last one is what we get when we plug in 3 for x. So I have these 7 equations here and 4 unknowns. This is an overdetermined system, and we know that overdetermined systems tend to have issues with solvability because we usually have too much information. And in fact, it's easy to see in this case that this is not going to be consistent. And that's typically what happens is these systems, overdetermined systems, are not consistent. Notice those two equations are different. I mean, basically the left-hand sides are the same and the right-hand sides are different, so they can't possibly be satisfied at the same time. So at best, we're going to find a least squares solution. All right, so our A is a 7x4 matrix. So we would have -1, 1, -1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 1, 8, 4, 2, 1, 8, 4, 2, 1, 27, 9, 3, 1. That's our A. Our B is just the constants. 7, 2, 1, -2, -1, -2, -18. We're trying to find the ABCD that best fits. That gives us a polynomial of best fit. It gives us the least squares polynomial. All right, so then our solution for our x, which means we're going to find the A, B, C, D, according to the formula, is A transpose A inverse times A transpose times B. That's how we find it. This is a very, very good calculator problem. So let's see if I can go over to calculator. I'll use I for the first one. It was 7x4. Our first one was, if I go back, should have been -1. Yeah. Should have been -1, 1, -1, 1, 0, 0, 0, 1. Oh, apparently I'm changing my A. I didn't want to do that. Did I? No, A is fine. 0, 0, 0, 1. It was the other ones I don't want to change, I think. Hopefully I didn't mess up my example for earlier. The next row was 0, 0, 0, 1. The next row was 1, 1, 1, 1. The next row was 8, 4, 2, and 1, and so was the next row. And the last row was 27, 9, 3, 1. That was our A. Let's edit our... I think I'm okay with the other matrices. Let's edit 9. It was a 7x1. And those constants were 7, 2, 1, 7, 2, 1, -2, -1, -2, -18. All right, now we got the stuff typed in. We want A. Make sure everything works this time. Transpose A. Oops, I don't need to do that. I can do it that way. Inverse A transpose B, which was I, and gives us that. And again, if you really, really want, you can change these to fractions probably. There you go. So in this one we get, see if I can shrink this. No, never mind. Negative 19 over 12. It was something over 108. Remember that much. 361 over 108, negative 50 over 27, and the last one was 35 over 54. So our least, what that means is that our least squares cubic is negative 19/12 x cubed plus 361 over 108 x squared minus 50 over 27x plus 35 over 54. That's our least squares cubic. And I did not plot this for you to show you what that looked like. So, let me see if I can do that real quick. Let's try a slightly different program here to do that. I just want to show you what the picture looks like. So, let's see if I can remember some of these points here. There we go. One of them was what? It was -1,7, I think was one of the points. You can see it plots the point up nicely. I think we had, what, 0, 2. No, it's not putting it in there. 0, 2. And I think we also had 0, 1. And we had 1, -1? No, what was it? It was 1 something. Sorry. It's hard to remember. 1, -2, that was the problem. It was 1, -2. We had, I believe, 2, -1. And we had 2, -2. And we had 3, -18. It's just not on the screen, but that's okay. Then we just had the polynomial. It was y equals -19 divided by 12 x cubed. That was weird. I must have hit the enter key. Sorry. Let's see if I can delete this out. There we go. We had y equals -19 divided by 12 times x cubed. And it was plus 361 divided by 108 times x squared minus, it was 50 over 27 times x. And then I don't know if I can see the other. Oh, I can. 35 over 54. Oops, and let me do it. Let's see if I can edit it. 35 over 54. Oh, there it was. There it is. Sorry about this. I don't have the keyboard up. It's a little harder to grab it. There we go. Plus 35 over 54. Excellent. Okay. Back to what we were doing. Here we go. And now we can see the whole point of doing this is I wanted you to show that, notice it's got pretty close to the A and the E and the F here. We're doing a cubic, so it's having a hard time bending to get that D. So that's one of the reasons why if we're using the cubic through these points, it's having to bend and not getting a good job to try to get these points approximated as well. But again, the idea is it's trying to get this error to be as small as possible. If it gets close to this one, it's going to get farther away from a different one. But that's what your least squares cubic would look like in this case. I wanted to show you a graph, and it took me a little while to get it entered, but at least you can kind of see what's going on there. All right. We don't just have to use linear functions, though, to do least squares if we're able to convert the functions into a linear one. All right, so to try to be as topical as possible here, let's look at coronavirus data for the U.S. here. Okay, so this is total U.S. cases from March 1st to March 27th. So almost the entire month of March. And it says find a function that looks like an exponential growth function, y equals ae to the bx, that best fits the data. All right, that's not linear in the coefficients. In particular, the b is up there in the exponent. However, we can convert this to something that's linear in the coefficients by taking the natural log and then using the log properties. Logs break up over a sum, and certainly the log of e to a power is just the power. So we get natural log of y is log of a. That's just a constant. So we're going to treat it as a constant to start with. And then bx. Okay. So the way we're going to form this particular one now is that I'm going to treat, like I said, I'm going to treat this like it's a constant. I'll have to figure out a separate after I'm done. And then I can figure out the b. What I'll have to do when I'm making my matrices, though, is make sure I take the log of the input, or the output, I mean. All right, so let's just say that this is x equals 1, so I can just put in the numbers 1 through 27. Your matrix A will have 1s down the first column 27 times, because when I put in a number for x, this number doesn't change. I probably shouldn't have called this a big A. I should probably call this a big B or something. Then over here, when I put, B is probably not the best letter either with that little b there, but we'll live with it. When I put over here, I'm putting numbers in for x and getting the coefficient for b. So over here, I'm going to have a column that's 1, 2, 3, 26, 27. Okay, that's my matrix A. My matrix B, my vector B, I mean, will be the log of the outputs. For the first one, it'll be log of 69. For the second, it'll be the log of 89. The third one will be the log of 103. Log of 69, 194. Log of 85, 991. So this is now when we would want to find our least squares solution. We would still do A transpose A inverse times A times B. A transpose times B. I think, if I remember correctly, that I already have all of these typed into these matrices, which is why I didn't want to touch them. So let's look at the matrix G here. There were our inputs, and if I scroll down, I can see that I really do have all of those in there. If I do my matrix B, I'm pretty sure I have the logs of those values there. All right, so, oops, parenthesis, matrix G transpose times G inverse times G transpose times B. So I really do have B there. All right, so those are the values that we have for log of little a and little b. Okay, so going back over here, log of little a because that was the first one that's in our, notice that that's what we left that capital BB, if you think about it as a constant. We have log of little a is about 3.77, and little b was about 0.28. Okay, so if I actually want a, then I would do e to that power, whatever that happens to be, but my b would still be the 0.28. So I didn't write out all the decimals, but this would be e to the 3.77 times e to the 0.28x, or I could write it all as one big exponent. And this would be my least squares exponential that best fits the data. Now I know that if you've used the TIs before, it'll actually do this. If you do your least squares approximation for this, if you've used the TI before, it will actually give you that exact same solution that we just found. All right, so how good is this? Well, let's look. All right, so I don't think I want, did I save it as F? Let me go back over and make sure that I actually saved that as F. 2 by 1. I bet it is F. All right, so in my matrix F, I saved the solution that we just found, the 0.38 and then the 2 point, whatever it was, the 0.28 and the 3.77 numbers. I've actually saved that in F. All right, so go back up here, not there, here. So I saved those numbers in F. We did e to that first one. So this notation here, when I have the matrix and then I have the 1, 1, you can actually reference the actual entry of the matrix. So I'm doing e to that natural log of a that we found, and then e to the bx. That's what this notation is. So when I graph, look at this. Look at how good that line, these points are those individual points that are in there. So we really are seeing an exponential growth in the cases, which is what you heard about in the news. So this is, and actually if you compute an r squared on this, the r squared is really, really high. It's like 0.9 something silly. I mean, it's a really, really good approximation for what's going on, which is cool and frightening at the same time, if you will. But here's some good news. So I did this from March 1st to March 27th on purpose, because if I scooch this window out to March 31st and compare the actual numbers for the next 4 days with what comes out of the model, we're going to see something a little bit different. Okay, so here are the points, and here's what the model says was supposed to start happening. So still going up, not necessarily a good thing. However, we really are bending the curve. You hear that in the news all the time of bending the curve. This is the model for the first 27 days, and it says we should have kept going up, up, up. We're not going up, up, up. It has slowed down. So at least from the actual data and from actually curve fitting, we can see that, hey, things have made a difference. Now, we don't want to stop, clearly, because things are still going up, but it's better than it was. And that's kind of the point of this. So anyway, hopefully this made a little bit of sense. Again, I apologize for all the issues this morning, and hopefully this will help you get started with these least squares problems.